Here is a lovely differential equation. We know how to solve this differential equation, do we not? We do. Well, you do if you've done the chapter on second order differential equations. We'd move the y to the other side, minus sine x. Then we'd have the auxiliary quadratic, which would be m squared plus no m minus 1 equals 0. So m would be plus or minus 1. That would give us a complementary function of y equals a e to the x plus b e to the minus x. Then we'd look at the right hand side and set up the particular integral, which would be an amount of sine x plus an amount of cos x. And then we would differentiate that, and we would differentiate it again, and then we'd stick it into the left hand side, and we'd find out what lambda and mu are, and then that would make our particular integral, and then we'd add that onto our complementary function, and we would get the solution. That would be fun. So, why am I not going to do that? Because I'm going to pretend for a minute that I can't solve this differential equation, and I'm going to show you another method where we can get an approximate solution. Here's the clever thing. I don't know what the solution to this equation is, but I know that it is a function. Why? That doesn't seem to be narrowing it down very much at the moment. But I also know that all functions y can be approximated using their Taylor expansion. Well, let's use f of x since that's the notation we're used to. F of x will be roughly equal to, more and more equal the further we go, f of a plus f primed of a, x minus a, plus 1 over 2 factorial, f double primed of a, x minus a, squared plus 1 over 3 factorial, f triple primed of a, x minus a, cubed plus, etc. So, even though I can't find out what this actual solution is, I'm pretending I can't, actually I can, I'm pretending I can't, I could find its Taylor expansion, so long as I can find these ingredients. That's all I have to do, the ingredients of the sandwich. If I can find them, then I will be able to write down the Taylor expansion of this solution, and that will be an approximation to the actual solution. Okay, let's have a go at finding some of these ingredients. Well, what's A for a start? We've got some information over here that we've been given that we're allowed to use, and it's about what happens when x is naught. So the information is what happens with the y and dy by dx when x is naught. So we're focused at x is naught here. So our A is going to be 0. The whole thing is going to be focused at the point 0. So at this stage, Maclaurin's saying, oh, it's a Maclaurin expansion. But actually, I'm still going to call it a Taylor series. And I'm going to write it a bit differently because there aren't any f of x's here, are there? There's no f of x. There's no f of x in the information. It's y. We're using y, not f of x here. So I'm going to rewrite Taylor's expansion. I'm going to use 0 as my a, and I'm going to use a different notation. Y equals, now instead of f at the point naught, I'm going to say that this is y at the point naught. And instead of the derivative at the point naught, f primed of naught, I'm going to write dy by dx at the point naught. So you get used to this notation after a while. 1 over 2 factorial. Now this is the second derivative, but it's not the second derivative everywhere, it's the second derivative at the point naught. And then we've got 1 over 3 factorial, and then we've got the third derivative. So all I'm doing here is changing the notation into one that's consistent with the problem I've been given. Okay, let's see if we can find any of these ingredients to go into our sandwich. Okay, y at the point naught. Well, that just means when x is 0, what is y? But I've been told that. I've been told that when x is 0, y is 1. Okay, that wasn't hard. Y is 1. What about the next ingredient? dy by dx at the point naught. And that's saying when x is naught, what is dy by dx? And again, I've been told, hooray, 2, it's 2. So that's that done and that done already. Okay, what about the next thing? The second derivative at the point naught. I haven't actually been told what the second derivative at the point naught is. But, hooray, I've got this equation. I can use that equation, can't I? Because, look, d squared y by dx squared is always equal to y minus sine x. So, d squared y by dx squared at the point naught would equal y at the point naught minus sine of x of naught when x is naught. So, d squared y by dx squared at the point naught must just be y at the point naught, which is, because sine of naught is naught, and we know that y at the point naught is 1. So I've done. It's 1. That's that one done as well. Okay, how many to go? Well, obviously infinitely many. That was a silly thing to say. But how many more until I'm up to my x cubed? Because that will do. That's a good amount of expansion. Oh, I need one more. Okay, now this is not good. Because I haven't got an equation that says the third derivative in terms of other stuff. But couldn't I just differentiate both sides of this? Differentiate that, get a third derivative, differentiate that. Then I'd have the third derivative with some other stuff, but I know the other stuff, so then I can find the third derivative at that point. I think this is going to work. Let's try it. D cubed y by dx cubed is equal to dy by dx minus, because we're differentiating with respect to x, minus cos x. So d cubed y by dx cubed at the point 0 will equal dy by dx at the point 0 minus cos of 0, which is equal to 1 minus 1, which is 0. Yay, I've got that one as well. Okay, so what did I get? This one was 1 I was told in the question. This one was 2 I was told in the question. This one was, oh, now I've forgotten. It was, well, that is equal to that minus that. That at the point 0 is 1. That's 0, so that was 1. That was 1. So I didn't get told that in the question, but it wasn't a huge amount of work to get it, was it? I just had to put my information in there. And then in order to get the last one, which came out to be 0, I differentiated the original equation, shoved everything in, and then I had it. So the bottom of my sandwich is y equals 1 plus 2x plus 1 over 2 factorial x squared plus 1 over 3 factorial times 0. So that bit goes, and I get this quadratic approximation to the solution. And if I knew what the true solution was, then I could plot this quadratic on top of that and see how similar they really are. Okay, let's try to do this one a bit more neatly. I'm going to make a sandwich because I'm doing Taylor. I'm going to write Taylor out in the way using the y notation. Normally it's f of a, so this would be y at the point A plus dy by dx at the point A, x minus a, plus 1 over 2 factorial d squared y by dx squared at the point A, x minus a squared, plus 1 over 3 factorial d cubed y by dx cubed at the point A, x minus a cubed, plus blah blah blah. Now A is our point of focus, and in this question we're given information about the point x is 1. When x is 1, we know y, we know dy by dx, x is 1. So in this question A is 1, and our ingredients are going to be y at the point 1, dy by dx at the point 1, d squared y by dx squared at the point 1, and d cubed y by dx cubed at the point 1. Now how much of this are we told in the question? Usually it's the first couple. Yep. Y at the point 1 is 1. dy by dx at the point 1 is 2. 1, 2. Halfway there already, and we haven't even done any work. Next bit's pretty easy too. Let's take that original equation, d squared y by dx squared plus 2 dy by dx equals xy, and let's just evaluate everything at the point 1. At x is 1, at x is 1, at x is 1, x is 1. Now d squared y by dx squared at the point 1 I don't know. In fact, that's what I'm trying to find. That's my next ingredient. But I do know what dy by dx at the point 1 is. It's 2. So this is 2 times 2, and this is equal to 1 times y at the point 1, which is 1. So that gives me d squared y by dx squared at the point 1 is equal to 1 minus 4, which is minus 3. One more ingredient to find. This takes a bit of room, so I'm just going to move that out of the way. So, what did I just find out? I found out that the second derivative at point 1 is minus 3. Now, to get the next one, I'm going to have to differentiate my original equation. So I start with my d squared y by dx squared plus 2 dy by dx equals xy, and I differentiate everything. D cubed y by dx cubed plus 2 d squared y by dx squared equals product rule. Hold the x still, differentiate the y, plus hold the y still and differentiate the x. Then evaluate everything at the point 1. X is 1, dy by dx at the point 1, y at the point 1. What does that give me? D cubed y by dx cubed at the point 1 plus 2 lots of, well, the second derivative at the point 1 I just worked out was minus 3, is equal to 1 times the first derivative at the point 1, which is 2, plus y at the point 1, which is 1. So d cubed y by dx cubed at the point 1 equals 2 plus 1 plus 6, which is 9. Hooray! Let's shrink that down. Oh dear, it's taking the minus 3 with me. I'll have to put that back in. So what have I got? That was minus 3. This is going to be 9, and I'm ready to do the bottom of my sandwich, the piece of bread. The solution is y equals, then I've got my first ingredient, y at the point 1, that's 1, plus my second ingredient, dy by dx at the point 1, times x minus 1, plus my third ingredient over 2 factorial, and that's times x minus 1 squared, plus my next ingredient, and that's over 3 factorial, x minus 1 cubed. And obviously the true solution, to get the real true solution, we'd have to do infinitely many terms, but this will be a good approximation to the solution to the equation we've been given near the point 1.